Okay, so I'm happy to start the highlights of algorithms 2020. So this is the first virtual conference of highlights of algorithms. But by now, I guess that most of us used already to virtual conferences. And we know how it works. We still decided that the invited talks are all going to be live because people prefer it, it looks like, but all of them are going to be recorded, so you can see it later as well. And as you probably already know, the typical thing is that all of us are on mute during the talk, and questions will be through the chat box, and then the session chair will read the question at the end of the talk, and this is how questions are going to answer. There is also the option of asking more questions later using the Slack. And without further ado, I'll switch already to Fabrizio Gandoni as the session chair of the first session. And yeah, I'm happy to see that we have already more than 100 participants. So Fabrizio, go ahead.
Thank you very much. So welcome everybody to the first session of this of ALG 2020, and the first speaker is Shay Solomon from Tel Aviv University, and he will speak about truly optimal Euclidean spanners. So please, Shay.
Hello, everyone. Can you hear me? Okay. So it's a pleasure to speak in this conference. This is joint work with Angle, and I'm going to tell you about recent progress on Euclidean spanners. So what is a Euclidean spanner? It is a special type of spanners where the input graph is induced by a set of points in the plane, or more generally in the space RD. So we have a set of points S, and you can see the bottom part of the slide for some examples. So this example is for the plane, and we implicitly consider the complete Euclidean graph induced by the point set. That's denoted by G of S. And now we say that H is a 1 plus epsilon spanner for the point set S. If first of all, it's a spanning subgraph of G of S. Let me also mention, maybe it's clear, but G of S is a complete weighted graph where the vertices are the points, S, and the edge weights are the Euclidean distances. Okay, so H is a spanning subgraph of this complete graph. And it is a 1 plus epsilon spanner if it preserves all the pairwise distances to within a factor of 1 plus epsilon, which means, in other words, that we would like for any 2 points P and Q to have a path in the spanner between them of total weight, meaning the sum of edge weights in the path, at most 1 plus epsilon times the Euclidean distance. And if we have such a path for any 2 points, then we say that this is a 1 plus epsilon spanner. This parameter, there's some delay here, is called the stretch, and we would like to get stretch arbitrarily close to 1. So in the bottom right part, you see an example for a 1 plus square root 2 spanner. This is not what we are looking for. We would like 1 plus epsilon stretch, where epsilon is very close to 0. And yeah, I'm going to talk usually about points in the plane, but almost everything generalizes to higher dimensions. Okay, so besides stretch, the most basic parameter of a spanner is the size, the number of edges in it, and we can consider a normalized notion that's called the sparsity. The sparsity is the number of edges in the spanner divided by n minus 1, the minimum size of any connected graph. Ideally, we'll have constant sparsity. And then a generalized parameter is the weight, the sum of edge weights. And here too, we can consider a normalized notion that is called lightness, the ratio between the weight of the spanner and the weight of the minimum spanning tree. And here too, we would like constant bound. We would like spanners with constant lightness ideally. And there are other parameters, but we are going to focus on these two. And more precisely, we would like to understand the trade-off between the stretch, 1 plus epsilon, and the sparsity, or between the stretch and the lightness. And we are going to focus on the regime of very small epsilon. It's a sub-constant parameter and constant dimensions. So why should we care about this? One reason might be in the application side. So light and sparse spanners find various applications, and in some of them, we really care about 2 and 3 dimensions and of very small epsilon. The smaller epsilon is, the more precise we get in many cases, and the performance will depend on either the sparsity or the lightness of the spanner, or on both. So obviously, we would like to try and improve upon these parameters as a function of epsilon and the Euclidean dimension. Okay, so now what's known? For the sparsity, there are several constructions from the 80s that all give a sparsity of epsilon to the 1 minus d. This is true for any set of points in RD for any d and for any epsilon, but it wasn't known if this is tight even for points in the plane. Maybe we can improve the sparsity in the plane from 1 over epsilon to, let's say, log 1 over epsilon. We didn't know if this is possible or not, and we'll see in a few moments that it's impossible to do any better as long as the dimension is constant. Okay, so this is for the sparsity. For the lightness, here there are less relevant constructions, and the most well-studied one is called the greedy spanner, and I wrote the pseudocode. It's a very simple construction, but analyzing it isn't so simple. And so the state-of-the-art lightness bound by Narasimhan and Smid is epsilon to the minus 2d. This is true for any set of points in RD and for any epsilon. It was an improvement over several works. I wrote some of them in this slide, but not all of them. And here there are there is some lower bound for a related structure that's called shallow light trees. Together with Elkin, we gave a lower bound for points in the plane. The lightness lower bound was 1 over epsilon, and it directly applies also to Euclidean spanners. But you can see right away that there is a big gap, even for this 2-dimensional case, there is a big gap between 1 over epsilon and 1 over epsilon to the 4. And so can we do better? And in particular, can we improve the lightness bound epsilon to the minus 2d? And here we'll see that the answer is yes. We can do much better. And so now let's see the precise statements of the results. So for the sparsity, we show that there exist point sets in RD for a constant d, so that any 1 plus epsilon spanner has a sparsity of at least epsilon to the 1 minus d. This is true for essentially any epsilon. We just need to make sure that epsilon is not too close to 0, because then the sparsity lower bound will be super linear in n, and this doesn't make sense. But other than this natural restriction, we don't need any quantifiers. So usually I'm going to omit such quantifiers in the rest of the talk. So this is a negative message. We cannot do any better for any constant dimension, but we also give a rather positive message. Using Steiner points, meaning points that are not in the input points at S, but they are lying in the same Euclidean space, we can get a quadratic improvement for the sparsity. So whatever was known before, we get essentially square root of that. So the sparsity bound using Steiner points is epsilon to the 1 minus d over 2 times some log factor. And for the two-dimensional case, we also show that this is tight. So one cannot do better using Steiner points than square root 1 over epsilon. Here too, we are hiding a logarithmic term. So every tilde that we'll see is going to hide a log term. Okay, so this is for the sparsity. For the lightness, the previous upper bound was epsilon to the minus 2d. It's by analyzing the greedy spanner. As I mentioned, what we show is a different analysis for the same greedy spanner that gives a quadratic improvement on the lightness. So what we get is epsilon to the minus d times some log factor, and we are not using any Steiner points for this. So it's just a different analysis for the same greedy spanner. And here too, we show tightness. So there exist point sets in RD for any constant d, such that any 1 plus epsilon spanner for this point set will incur a lightness of omega epsilon to the minus d. To summarize, we get tight bounds up to log or polylog terms for any constant dimension d. And in particular, we get a quadratic improvement over the state of the art for both the sparsity and the lightness. And interestingly, we are using Steiner points to reduce the sparsity, and this is mandatory, but we are not using Steiner points for reducing the lightness. And this is quite surprising, because if you think of the standard usage of Steiner points, this is probably for the Steiner minimum tree problem, where you have a set of points, let's say in the plane, and you would like to connect them by some tree, and it's beneficial to add Steiner points. It will reduce the weight, but inherently, it will increase the number of edges. It will increase the size. What we are showing is, in some sense, opposite. We can use Steiner points to reduce the number of edges, but we didn't use them to reduce the lightness, the weight. And the last takeaway message is that the greedy spanner without Steiner points is optimal both for sparsity and for lightness in any constant dimensional space. And this is a refinement of the previous work with Filzer, where we showed that the greedy spanner is essentially just as light and just as sparse as any other spanner, but there was a constant in the exponent of both the size and the lightness bounds. So now the starting point of this work is with a very simple observation, almost trivial, in the lower bound, on the lower bound side. So now I'm not using Steiner points yet. We identify a Hardy instance, the d-dimensional sphere. And let's start with the two-dimensional case. Here we have a circle, and we are placing roughly 1 over epsilon points on the boundary of this circle. They are going to be evenly spaced. So if this is a unit circle, then the distance between consecutive points will be roughly epsilon. Let's say c times epsilon for a big enough constant c. And then the observation, which by the way, builds on previous observation for shallow light trees in the paper with Elkin that I mentioned. So the observation is this: consider any 1 plus epsilon spanner for this particular point set. Then it must include all the edges of weight bigger than square root 2. Okay, so in other words, if there are 2 points, P and Q, that are a distance bigger than square root 2 of each other, then there must be a direct edge between them in any 1 plus epsilon spanner. Because if there isn't a direct edge, let's look at the shortest path between them in the spanner. It goes through at least one intermediate point. Let's call it X. Maybe many, but at least one. So by the triangle inequality, the spanner distance between P and Q is bigger than the Euclidean distance between P and X plus the Euclidean distance between X and Q. And now we need to use some geometric properties. X and Q are pretty far from each other. They are at least C times epsilon apart. And P and Q are very far from each other. And now all these 3 points lie on the boundary of the circle. And then simple trigonometry will give us that this sum of Euclidean distances is just too big. It's bigger than 1 plus epsilon times the Euclidean distance between P and Q. And it means that there must be a direct edge between P and Q. And so the corollary is any 1 plus epsilon spanner for this point set must use omega 1 over epsilon squared edges, at least, all of which have weight at least square root 2. And this essentially concludes the lightness argument, because we just need to realize that the weight of the minimum spanning tree here is constant. It's slightly smaller than 2 pi. And this point set doesn't include endpoints, maybe, but we can add points until we get endpoints that coincide with the 1 over epsilon points that you see here on the boundary of the circle. It doesn't change anything, not the lightness and not the geometric inequalities that we had before. For the sparsity, however, we are not done. We cannot just add more points until there are n, because the sparsity will decay. We just need to use roughly epsilon times n vertex disjoint copies of the same example, and to spread them sufficiently apart from each other, sufficiently far from each other, and then the lower bound will scale smoothly. Okay, so this is for the 2-dimensional case. We then generalize these ideas for the d-dimensional case, and we also need to rely on some classic packing arguments. It's known that the maximum set of vectors that we can pack into the unit sphere, such that the minimum angle between any 2 vectors is at least epsilon, is theta of epsilon to the 1 minus d times some another term that depends exponentially on d, but for constant dimension, this is what we get. And this allows us to conclude the claimed sparsity and lightness lower bounds that we see here in the bottom part of the slide. For the sparsity, this matches precisely the classic sparsity upper bound, but for the lightness, this is just the beginning. Okay, so we have a lower bound of epsilon to the minus d, but the upper bound is far, and we want to reduce it quadratically. And this is quite a challenge, and I'm going to talk something like a minute or less in the next slide about this particular challenge. Right now, I want to spend 5 minutes or so on the upper and lower bounds for Steiner spanners, because this is what I view as the highlight of the work, the fact that we are using Steiner points in an unexpected way to reduce the classic sparsity bound. Okay, so the upper bound construction that I'll describe very, very briefly is going to be for 2 dimensions, but the ideas carry over to any dimension, even super constant dimensions. And the strategy is very natural. We start with a warm-up observation, a very specific point set, and then we generalize it in a few steps. Okay, so what is this point set? Instead of considering point sets lying on the boundary of the unit circle, we are going to consider point sets lying on the boundary of the unit square. It's just more convenient for upper bounds. But it's the same situation. Okay, so the distances between consecutive points would be roughly c times epsilon, and the number of points that we are spreading here is going to be roughly 1 over epsilon. And then we consider the points on the upper and lower sides of this square. And by the same argument as before, we can say that any 1 plus epsilon spanner for this square instance must include all the edges of the complete bipartite graph that you see in the bottom right part of the slide. Because if even one edge is missing, the stretch will be bigger than 1 plus epsilon. So this is something that we know already. Now the trick is to use Steiner points. So we are taking straight horizontal line in the middle of the square, and we are spreading roughly square root 1 over epsilon Steiner points there. They are going to be evenly spaced with distances roughly square root epsilon from each other. And then we just replace the complete bipartite graph that we had before by a new one between the Steiner and the non-Steiner points. The upper right part of the slide. So it's still a complete bipartite graph, but it's much sparser. So in this way, we reduce the sparsity from 1 over epsilon to square root of that. And it's a simple exercise to see that the distances remain roughly the same. So we still get the 1 plus epsilon spanner, but then this is a very specific point set. Now we would like to generalize it. And the first observation is that we don't have to really take a square. We can consider a rectangle with sides, let's say 1 and 1 over k. And k could be a big integer. And then the bigger k is, the more Steiner points we need to throw in the middle of this rectangle. So the sparsity grows accordingly. And in fact, we can even move points from the boundary of this rectangle pretty far away, actually. So this gives us some slack. So I'm going to call this the warm-up construction. And then in the next step, we employ it to handle point sets of bounded aspect ratio. So the aspect ratio of a graph or of a metric is just the ratio of the maximum to the minimum pairwise distances. So let's denote it by delta. What we are doing here at a very high level, we divide all the pairwise distances to a logarithmic in delta buckets so that the ith bucket is roughly distances 2 to the I. And then we take a big enough square enclosing all the points. We subdivide it into subsquares of side length theta of 2 to the I, the distance scale that we care about. It is important to make sure that those subsquares overlap. In this way, it allows us to be able to handle each square separately. And then we subdivide the squares into appropriate rectangles, and we carefully apply the warm-up construction. That I will not go into the details, of course, but we need to be careful in the way we are employing the warm-up construction, and this gives us the construction for point sets of bounded spread. But notice that the spread could be really huge. There is no way to bound it in general. And so the last step is to reduce the general point set to point set with aspect ratio, let's say 1 over epsilon. And this part I will skip. I'll just say very briefly that we employ several ideas from the area of spanners in doubling metrics, where doubling metrics is a generalization of Euclidean low-dimensional metric spaces. And then we combine them with some new ideas, and this is how the reduction works, roughly speaking. And now for the lower bound, very quickly, I'll just say that this is a technically challenging part of the paper. And intuitively, the reason this is non-trivial is because it's non-trivial to reason about points that are not part of your input. So what we would like to show, and this is just for the two-dimensional case. The three-dimensional case and higher dimensions are open. What we show is that any Steiner spanner for the square instance has sparsity bigger than roughly √1/epsilon. This is essentially what we are showing. And the square instance is not the same square as we had before. It's a sparser instance. We make sure that the number of input points is not 1/epsilon, it's square root of that. So they are farther away from each other. Their distances are at least square root epsilon rather than epsilon. And then, in a sense, Steiner points will not help us much in this sparser instance. So to prove this lower bound, we actually prove a lower bound on the weight of any Steiner spanner for this square instance. We would like to prove that the weight of any Steiner spanner is at least 1/epsilon. If we can show that, the sparsity lower bound will follow. So how can we prove that the weight is 1/epsilon roughly? So what is this 1/epsilon? It is the number of pairs of points in this instance. And I'm just going to give one slide with the key idea. The number of pairs of points, let's say x1, x2, where x1 is in the upper part of the square and x2 in the lower part, the number of such pairs is, as I mentioned, 1/epsilon. The shortest path in the spanner between any such pair of points is a distance at least 1. So if we could argue that those shortest paths do not overlap, they are completely disjoint, we will be done. Because it will mean that any shortest path contributes a fresh unit of weight, and overall it gives us 1/epsilon. The problem, of course, is that these paths could have significant overlaps. Okay, so let's look at two shortest paths, qx and qy. Qx is the shortest path between x1 and x2, and qy is the shortest path between between y1 and y2. I need to finish very quickly. If the distance between xy and y1 is bigger than j times square root epsilon, and likewise, if the distance between x2 and y2 is bigger than that, then we can argue that the amount of overlap is at most 1/j squared. These paths could overlap, but very slightly, and this amount of overlap decay inverse quadratically in this parameter j. And using this key lemma, we can prove the lower bound, but of course, proving the lemma is not so simple. And now, less than a minute, I want to conclude with this last challenge that I didn't go through, is to reduce the lightness of non-Steiner spanners from epsilon to the -2d to epsilon to the -d. The proof that we used is complex and technically very elaborate. For that reason, it was difficult for us to further improve this lightness bound using Steiner points. We wanted to get something like square root of epsilon to the -d using Steiner points, but it was very difficult because the proof was so complex. So recently we gave a simplified argument, which is part of a unified approach. Let me tell you very quickly about a couple of advantages of this unification. First, we can get improved constructions of light Steiner spanners. Second, we can get improved lightness bounds for several other graph families, including minor free graphs and general graphs. And let me emphasize that for minor free graphs, we get an optimal trade-off between the stretch, 1 plus epsilon, and the lightness, which is the size of the minor over epsilon plus 1 over epsilon squared. And interestingly enough, the lower bound that we are using is Euclidean graph. So there are some connections, intimate connections to what we are doing here. And finally, we are able to get faster running times for constructions of light spanners. And here I will just highlight the result for general graphs. We get a linear time construction with essentially the optimal lightness bound. When I say linear time, I mean linear in the number of edges, provided that this number is slightly super linear in n. So if the number of edges is bigger than n log star n, slightly bigger than n, we get the linear time construction. And this is a significant improvement over the previous work. So I'll stop here. Thank you for your attention. Any questions?
Thank you. So the audience was supposed to write questions on the chat. Maybe this was not very clear. So I don't see any question at the moment. Maybe something quick. If not, since we are a little bit late, I would proceed with the next talk, and I will thank Shay for the nice talk.